Welcome back. This is lecture 34. So let's continue our discussion on mixers. So in today's lecture, what I would like to do is to start replacing those switches with transistors and then see what are the potential impacts and how to go about biasing the transistors, right? So let's start off with the assumption that we have an LNA, right? We know how to design an LNA. LNA is typically they used to have at the output stage your LNA had a LC, right? And this was connected to VDD. And now we are saying that we are putting a mixer. By the way, when we are talking about passive mixers here, where the idea is there need not necessarily be a DC current through the mixer. Okay. So what we are interested in passing the input signal at RF and not necessarily at DC, right? So what we can do is to understand the fact that the DC voltage at this node is VDD, right? So this is the DC voltage, or the quiescent voltage at this node is VDD, and we have to put a switch, right? I'm showing at present one switch, but you can assume that there will be multiple switches that will follow. Now, what are my options of making a switch? Note that I am doing this in a CMOS technology, so I have two options. I have either NMOS or a PMOS. So if I use an NMOS switch, this is my option, and if I use a PMOS switch, this is my option. And how do I turn a switch on or off? So I'll have to probably put a clock here which goes from maybe 0 to VDD, right? When the gate is 0, right, then definitely the gate to source voltage is either 0 or negative depending upon what the source voltage is, which means the transistor is off. And when the gate is VDD, assuming that the VGS is higher than threshold voltage, then the transistor is on, right? Similarly in this case, so by the way, in this case VDD means on, in this case 0 means on, correct? So now, given that we have two options, I can go choose NMOS or PMOS, which one we would like to choose. If I do not have any other information, generally one would go about choosing an NMOS simply because NMOS has a larger driving strength, right? Or in other words, for the fixed amount of, since the mu n of an NMOS is higher than mu p of a PMOS, right? Which essentially means that for the same amount of size, right, same W by L, the on resistance of a NMOS will be less than the on resistance for PMOS. Now, how do we figure out what is the on resistance? So for on resistance, we understand that a switch, when it is on, right, will act in a linear region, right? So when on, the switch should be biased in linear region, which means its current voltage characteristics is mu n Cox W over L VGS minus VTH whole squared, VGS minus VTH times VDS minus half VDS squared, which means the on resistance, right? If I assume that it's an extreme inversion, extreme linear region, then I can basically say this is equal to mu n Cox W over L is V over drive times VDS, which means the on resistance R on is 1 by mu n Cox W by L times V over drive. Okay. So since in case of an NMOS, your mu n is greater than mu p, and Cox and V overdrive are kind of, Cox is kind of same, and V overdrive you would like to maximize. That is, you would like to have whatever maximum V overdrive that you can have in an NMOS will be the same as in a PMOS, which essentially means that for same W by L, you are going to have lower on resistance for an NMOS than a PMOS, and hence yeah, you would like to prefer an NMOS transistor. But having said that, you might say, why not? What's the problem if I simply increase W by L? Yes, if you simply increase W by L, you are going to have it is possible to reduce the on resistance of a PMOS transistor also, but you have to pay because there is a capacitance associated of increasing the W, right? The moment you increase the W, you make the transistor bigger, which means there are clock drivers which are driving the mixer switches, right? And the point that I'm trying to make here is, how do you get these square wave switches? How do you get these square wave clocks? These are normally fed from some sort of oscillator, right? Some sort of oscillator is there, and the output of the oscillator you buffer by a set of inverters, right? And generally, depending upon whatever capacitive load that you are driving, you size the inverters bigger and bigger. Otherwise, you are going to have a shallower rise and fall times, right? So I think we have done this in our UG level digital electronic courses, right? So where we understand the fact that the power consumption, if I have a capacitor C and if I have to switch it, the power consumption associated with the capacitance is C VDD squared F, right? Where F is the switching frequency. So naturally, if C is high, your amount of power consumption that these inverter chain will have to deal with will also be high. And naturally, when the inverters are driving bigger and bigger capacitances, they themselves have to be bigger so that they can ensure the rise and the fall times are small and the waveforms are nice and sharp, which means that burning a lot of power, right? So you do not want to, unless there is a pressing reason for using a PMOS transistor for a switch. Sometimes there are. You wouldn't want to use a PMOS transistor for a switch, right? Okay, fine. So having established the fact that we want to use an NMOS transistor for a switch, so how do I go about biasing it? So note that if I connect the LNA here out directly, so this node is always at VDD. If that is at VDD and this node goes from 0 to VDD, right? So the switch is always off, right? So this doesn't make sense. But we understand that I don't need to couple a DC current, right? I am not looking for any DC signal. My signal is at RF, which means that I can have a different bias for the mixer and for the LNA and AC couple them, right? And how can I do that? I can simply not connect them directly. I can connect them through a capacitor, just like we do any other analog circuits, right? So I call this C, let's say, right? Okay. But what about the biasing? How should I bias this node? Should I leave it floating? Clearly not, because if it's floating, then I don't know what's going to happen. But how do I bias this node? Should I keep it at 0 or should I keep it at any particular voltage? And if I have to keep it at a particular voltage, how do I connect it? Just like in any analog circuits, you connect it through a biasing resistor. Let me call this RB, and let this voltage be called VB. Right? Now the question is, how do you decide on VB? Can VB be 0? If VB is 0, what can happen? Note that this node is supposed to swing. Correct? If this node swings, which means this node is also supposed to swing. Now you do not want that node to go to negative. Why? Why not? Because if you recall, the body of this NMOS is always grounded, right? So if the source goes negative, then the PN junction associated with the source body or the drain body junction is going to get forward biased, and you are going to land up in trouble. So you have to ensure that this node voltage is not at DC but at a higher voltage, right? Okay. And it should be sufficiently high enough to ensure that the maximum lower side of the swing that you anticipate at that node gets accommodated for. Okay, so if you are starting off and if you do not have any idea what this should be, then VBB you can set it to be VDD by 2. That's one of the safe bet. Okay, so what about this voltage? Can this go from 0 to VDD? Sure, it can go to 0 to VDD. When this is at 0, right? When this is at 0, your overdrive is 0 minus threshold voltage, which is minus threshold voltage, minus VTH, right? When this is off. And when this is on, V overdrive is VDD minus, sorry, this is not 0 minus, you have 0 minus VB minus VTH, right? So this is negative VB plus VTH is your overdrive. When it is on, you have VDD minus VTH minus VB, right? So this is VDD minus VB plus VTH. This is the overdrive when this is on, right? So clearly it seems like, I mean, for the off case at least this is an overkill, because when it's off I would like it to be at 0 voltage, right? At V overdrive it's supposed to be 0. But if I switch the gates from 0 to VDD, then it looks like, I mean, when I get by with 0 V overdrive, I'm using negative VB plus VTH, right? So if, for example, if operating with VDD of 1 volt and VB is 0.5 volt and threshold voltage is also 0.4 volt, then this effectively becomes minus 0.9 volt. And when the transistor is on, I'm left with only 100 millivolt overdrive. I mean, that's probably for this type of biasing is over optimizing for the off state case and not really optimizing for the on state case, right? So what can I do? I can ensure that, I mean, all I need to ensure that this does not go from 0 to VDD, right? So this bias voltage goes from, let's say, 0 plus VB plus VTH to VDD plus VB plus VTH, right? So if I can ensure that, then I am done, right? So in that case, if this is the case, then what is the V overdrive during off state? Then this is obviously 0 volt. And what is the V overdrive during on state? This will be VDD, right? So you are this looks to be the best possible solution. So, but how do we go about achieving that? So here note that we have done this VB. So all we have to do is to again bias it with a VGQ and then feed your feed the 0 to VDD clock through the capacitor, right? So how do you decide what should be VGQ? So note that when what will be the voltage at this point? So note that the quiescent voltage at this point. So it might seem like the quiescent voltage at that point is VGQ, right? Which indeed it will be. The point that we need to understand is that if this is VG, so what will VG look like, right? So VG will go up and down from VGQ, right? So your VG will be somewhere around VGQ. It will go some up and down VGQ, right? But how much will it go down below VGQ and how much will it go above VGQ? How will you decide? The only way to decide is to understand the fact that the DC current to the capacitor is 0, correct? DC current through the capacitor is 0, which essentially means that, so before I assume that the output of square wave, let me ask you this question. So let's say I have a RC circuit similar to this. Let's assume this is like this. Okay, this is R, this is C, and for the purpose of this explanation, assume this is grounded. I mean, in our case, it is VGQ, but for the purpose of this explanation, assume this is grounded, and you have a square wave, 50% duty cycle, right? So, what will be the waveform here? Under the condition that your RC is much greater than this TLO. RC is much greater than TLO, right? So clearly, if RC is much greater than TLO at steady state, the capacitor, you can assume the capacitor to be almost behaving like a short circuit for the frequency of interest, which means waveform will retain its shape on either side of the capacitor, right? That much we can definitely say, right? So which means this side will also be this, right? Let's assume this side is going from what should I assume? Let's say this is V1 to V2, right? The question that we need to ask is, what will be this value and what will be this value, right? I understand the difference will be V2 minus V1, but what will be the exact value? So how do I go about thinking about it? So the way to go about thinking about it, I know that IDC through the capacitor is always 0, right? So regardless of whatever happens, if IDC through the capacitor is always 0, which means the V voltage that I through the resistor is also 0, which means VR should be 0. What is VR? Average, right? So VR DC should be equal to 0, right? Now what is VR DC? VR DC is nothing but the difference between, let me call this, should I call this V1R, V2R. So the average of V1R and V2R, right? Because this is a 50% duty cycle, so I know that the average is, in this case, V1R plus V2R by 2, right? So this should be equal to 0, correct? So which essentially means that the waveform that I am going to have here will be the average, which is the average value will be 0, right? And I know that this difference is V1 minus V2, right? And I know that this is equal to V1R plus V2R by 2, which is 0, which means your V1R is equal to minus V2R, which means it's symmetric about 0, right? So this and this are identical, which means that this guy will be negative of V2 minus V1 by 2, and the top side will be positive of V2 minus V1 by 2, correct? So which essentially means that in our case, when you have a voltage source VGQ attached to it, right? So this VG will be this V2 minus V1 by 2 is what? It's VDD by 2 in our case, right? So it will be VDD by 2 above and below VGQ, right? So this will be VGQ minus VDD by 2, and this will be VGQ plus VDD by 2. And what do I want the lower voltage to be? This I want to be equal to, this is the off voltage, this I want to be equal to 0, right? This I want to be 0, which means I will choose VGQ to be equal to, this is my choice, I will choose VGQ to be equal to VDD by 2, correct? So that would be the optimum biasing for this passive mixer. Okay. So the next thing that I would like to focus on is So by the way, I mean, if I have to complete the picture, what does the picture look like? So you have this LNA, and obviously LNA has an output impedance or output admittance. Let me put the Z, this here Z, then you put a capacitor, then you have this mixer switches. These mixer switches are biased with VGQ, the RB. This is also biased. Similarly, you have other switches, right? If you have IQ mixer, for example, sorry, if you have a double balance mixer, then you have 0 and then you have minus 90. Sorry, this is 0, this is 180, right? And then you have another LNA which with the differential polarity, and you have the same thing copied here, right? So this is plus, this is minus, and this is, so goes like this, and then you combine, right? Then you combine what the output is appropriately. Okay, if you are doing an IQ mixer, for example, then you require, if you recall the previous lecture, if you want an IQ mixer, you require 4 phases of clock. So they are not 50% duty cycle clock, they are 25% duty cycle clock. So if there are 25% duty cycle clock, the value of VGQ will change, because the average is no longer, will not no longer be V1 R plus V2 R by 2. So you have to adjust the value of VGQ accordingly. Okay, let's now start focusing on some of the other aspects of this passive mixer. So obviously, I mean, you cannot get away from the analysis of noise. So what I'll do is I'll try to give an intuition as to how to go about think about noise in case of mixers. So let's assume for the time being the transistor, let's assume it's an ideal switch. Okay. And you have LNA and everything connected on one side. And let's assume you have thermal noise. I mean, whatever you have on the left side of the mixer, you will have thermal noise associated with it, right? So let's assume you have input, you have thermal noise. Your thermal noise here. So my question to you will be, let's for the time being assume that this side is shorted for the purpose of discussion. Let's assume this is shorted, right? So my question is, what will be the noise current flowing into the short circuit? Right? So this is F, and this is switching at FLO. Correct? So how should I go about thinking about it? Just like if it were a signal, what would we have done? We understand the fact that the spectrum of the clock is something like this. You have a DC, which is which is which has a strength of C naught. Then you have FLO, which is C1. Then you have C2, and so on. Here you have C negative 1, and so on, right? And you are multiplying. This is Vn in, right? You are multiplying whatever comes in the input of the mixer port to the clock, right? So which essentially means that the spectrum gets convolved, right? The signals gets convolved in the frequency domain. Okay. So if we only had C naught, right? If we only had C naught, what would have happened to the spectrum, to the short circuit current? If we only had C naught, then the output would have been, this would have been C naught times the spectral density of the input, right? C naught, or the mod of C naught squared times spectral density of the input, correct? If I am talking about current, let me just leave it at the current domain. So let me call this IN in, yes, IN in. Okay, but so this would have happened because I am multiplying the spectral density of C with C naught squared. But because I have additional tones at C1, I will also multiply the spectral density with C1, right? And note that this is a shifted spectrum, which means the spectral density of the input will get shifted by C1 by FLO, correct? Will be shifted by FLO and then get added up. But if the input is a white Gaussian noise, then the shift wouldn't matter because it would all look the same, right? So essentially means that I am going to get a additional noise, and this will be this that the increase in the noise floor due to this will be C1 squared times S in I in. Similarly, I'm going to have for C2, I mean, if it's 50% duty cycle, C2 doesn't exist, but you get the idea, right? So you are going to have all of them added up. So you are essentially going to get ISC noise, power spectral density will be S in IN summation of Cn square and equal to minus infinity to infinity, right? So if it is a 50% duty cycle clock, then this summation essentially boils down to 1 over 2, you get S in by 2. But the key thing to note is that while doing noise analysis, you have to understand that there is the noise from noise due to different parts of the spectrum can fold back and come to the frequency of interest. Now, what is your frequency of interest? If you recall, our frequency of interest is around FIF, right, which is at a much lower frequency, right? So let's say my frequency of interest is here. Let's say this is FIF, correct? So around FIF, right? So I am getting stacking of these PSDs, correct? But what is this is as far as the noise power spectral density is concerned. Or what about the signal power spectral density? If you have a V in here, right? So, and if V in is at FLO plus FIF, right? So this guy is going to also create a noise component around FIF, right? And what will be that strength? The noise component for this will be C1 times the strength of the input, right? C1 times VPP, right? VPP over 2, if I say, correct? So, which essentially means that your signal to noise ratio at the mixer output, right? Your SNR is essentially C1 squared VPP squared by 4 by S in summation of n Cn squared, mod Cn squared, I should say, correct? The important thing to note here is that the signal is getting the component of the Fourier term for the mixer that is contributing to the signal is C1, right? But the Fourier terms that is contributing to the noise are all C's, right? So hence you have to be careful while doing a mixer noise analysis. You cannot really do it like a LTI transfer function, and you assume that you found out the transfer function corresponding to the signal, right? And that will also be the transfer function corresponding to the noise, because there is a harmonic folding from all multiples of your switching frequency back to wherever you are observing your signal at. Now some jargon, this value of C1, which is contributing to the signal, right? So this C1 or C minus 1, right? Or I should say C plus minus 1, because if you are considering both sides of the spectrum, is called the conversion gain, right? Another piece of jargon is the bands that arise because of these C0, C1, C2 and all. These are called harmonic bands. These are often called side bands. Okay. There are certain side bands that you would want. There are certain side bands that you will not want. But the key thing is to note is that when you do your analysis of mixer in a simulator, you will have to choose a sideband if you want to do your analysis, right? So when you are doing an LNA, for example, in your simulator, so you do typically, if you want to find out the transfer function of an LNA in a simulator, you do an AC analysis, right? When you are doing the similar analysis for a mixer, you will not be able to do an AC analysis, because in an AC analysis, the assumption is that there is no variation of it, it's an LTI system, right? So there is no second input, right? So in this case, we have you kind of have two inputs operating at different frequencies. So hence, you will not be able to do an LTI simple AC analysis. You will have to do a periodic steady state analysis, right? So you do periodic steady state analysis. From there, you have to tell the simulator, right, which is your desired band that you are interested in seeing, right? Because right now, if you tell the simulator, I want to see the band around FIF, it is going to collect the input from all across the spectrum, right, and show you how the input from all across the spectrum gets multiplied and gets overlapped onto FIF. Okay. Similarly, you can ask the simulator to show you what is the spectrum around 2FLO. So it will show you accordingly, right? So the key thing to note here is that you have to be mindful of the sideband that you are interested in. So in this case, for example, right, in general, your output is that the frequency of the output is that if I assume the LNA is perfectly linear, then the output will be at F in plus minus FLO, right? Plus minus MN FLO, right? So this is assuming LNA is perfectly linear, right? So, but if LNA is also non-linear, which is almost always the case, right? So then you are going to have harmonics of Fin. Then your output will be, so mixer output will have frequency of MFN plus minus NFLO. Correct? So then you have to tell the simulator that around which frequencies, by the way, this is due to distortion, and this is due to sidebands. Okay, so you have to tell the mixer which N basically you are interested in observing, right? So most simulators have an option to specify the N, right? So if you tell for example, if you are interested in finding out what is the conversion gain, then you tell the simulator the N is equal to 1 or minus 1, right? If you are interested in finding out what is the strength of the signal at, let's say, around FLO, right? Then, or rather, if the input is at Fin and you want to find out the strength of the signal around Fin at the output, then you say that your N should be equal to 0. But if your input is Fin and you want to find it out what is the strength of the signal around Fin minus FLO, then you have to tell the simulator that N should be equal to -1, right? Okay. So let's not digress further. So the next thing that we need to understand is if I have a thermal noise, so what is happening? Let's say I'm only interested in finding out the noise around FIF, correct? So what can contribute to the noise around FIF? The input has a noise spectrum, correct? Input has a noise spectrum, and which is white, which is all across, and my mixer has these tones, C0, C1, C2, and so on, and then similarly I have C minus 1. Let's only consider C0 and C minus 1 for the time being. Okay. This is at FLO, that's 0. So now, if I'm interested in finding out, so note that this is this. So what is happening? I'm multiplying in time domain. I'm basically, if this is a signal, which is not, ideally I should be using correlation, but assume it's a signal, then in the time domain I'm multiplying this this with this, right? So which essentially means that again same thing, you are going to have a convolution of the PSD, right? So which essentially means that whenever we get multiplied with C0, I get this, right? So but my frequency of interest is only around FIF. So even though I'm drawing the entire spectrum, I'll be concentrating around FIF. Then I'm going to get something because of C1, right? I'm going to get something because of C1. Then I'm going to get something because of C minus 1 also, right? I'm going to get something because of C minus 1 also. And the contribution of C1 and C minus 1 are identical, right? Because they have identical strengths. Okay. So if I take a differential output, right, then C0 is 0. So I can basically knock off that contribution of C0. But I'll get the output, I'll get noise due to both C1 and C negative 1, right? So your noise contribution is ESD of noise is basically because of C1 squared plus C minus 1 squared times S in, correct? But what about the signal? What about the signal? I mean, signal will only appear around FLO plus FIF, correct? So your signal will probably appear only at around, let's say, FLO plus FIF, right? So let's say this is signal, correct? So the negative frequency also I'm going to have signal. So this guy will get multiplied with this guy, and I will get this guy, correct? But there is no signal at FLO minus FIF, right? So at FLO, say at FLO minus FIF, there is no signal. Because there is no signal, this is not getting multiplied with plus FLO to create a tone at FIF. So at FIF, I am only getting signal contribution from one of the sidebands, but noise contribution from both the sidebands. Correct? So hence the noise figure, the noise figure, there are two types of definitions that are usually used for defining noise figure, because if I am only considering the signal contribution from one of the sidebands, then I am going to get a lower noise figure because my power of the signal is not doubling, but the power of the noise is anyways doubling, right? So hence there are two types of noise figures. One is called a single sideband noise figure. Another is called double sideband noise figure. This is all SSB. It's called DSB. And generally, I mean, if no other information is given, the single sideband noise figure will be higher, will be double that of the double sideband noise figure, because here the assumption is that signal is present at both sidebands at FLO plus minus delta IF. Should not say sidebands. Here the assumption is that the signal is present at both FLO plus minus FIF. Here the assumption is that the signal is only present at FLO plus IF or FLO minus IF, right? So in order to, so that is why your SSB side noise figure is generally 3 dB higher than the DSB noise figure. Okay. Okay. So before we wrap up mixers, let's quickly see what are the things that we looked into. So from starting, we looked into basics of mixer, right? Then we looked into the issue of image rejection, We saw there are two ways of dealing with it. One is put an image reject filter or do a IQ mixer. The part that we didn't cover was what happens in an IQ mixer if there is a difference in the gain and the phase between the two paths, right? In IQ mixer, you are, if you recall, we were kind of adding two paths with identical gains and 90-degree phase shift, right? But it is quite likely that they will never have identical gains. In fact, not likely. It is in practice. You can never have identical gains between two different paths. There will always be some error, and you'll never be able to get a 90-degree phase shift. There will be some error, right? So there will be some error when you do IQ mixer, and that error is also important. So that quantification of error is called image reject ratio, IRR, or image rejection ratio, which essentially means that it's basically the ratio of the strength of the image with the strength of the desired signal. Right? Ideally, you should not get any error, but in principle, you are going to get an error, and the quality of the IQ mixer depends on. I mean, one of the metrics of the quality of IQ mixer is what is the under the condition there is a gain imbalance between two paths and there is a phase imbalance between two paths. How much of the image signals retain and how much you do not have, right? So that is one. Then before image rejection, also we saw single balanced and double balanced mixers. Today we saw the effect of noise folding in mixers. We saw how to bias a passive mixer. We haven't covered active mixers in detail. I'll try to give you a brief flavor of active mixer. I mean, I talked about an active mixer is basically nothing but a current source followed by switches. But there are some other things that need to be taken care in an active mixer. I'll talk about it in the context of transmitter, because active mixers, as it turns out, are more popular in the transmitter path than in the receiver path. But I mean, you will be able to connect it to receiver also if as and when required, right? Okay. What about so by the way, let me just go back and see this part. Here I talked about this VGQ to be equal to VDD by 2, assuming that if VGQ to be equal to VDD by 2, the minimum signal, I mean the under this condition, so this is a continuation of the something that I left off. So I'm going back. So apologies for the back and forth. So if this is VGQ, then your VG min in itself is 0, right? So that is not what we want, right? So we wanted to ensure that your VG min is higher than 0. Otherwise, you are not optimizing it for the correct bias, right? So for that, what we needed to do, so your let's not say that your VGQ is equal to VDD by 2. Let's assume it is VGQ minus VDD by 2. So your VGS min becomes VGQ minus VDD by 2 minus VB, right? And we assume VB to be equal to VDD by 2, which is equal to VGQ minus VDD, correct? So your V overdrive minimum under quiescent condition, this is under quiescent condition, is VGQ minus VDD minus threshold voltage, right? Okay. So at the worst case, what you would like to have is as the under quiescent condition, right? So your when the clock swings, right? So this should be equal to 0, correct? So your VGQ should be equal to then VDD plus a threshold voltage, right? Okay, not VDD by 2. Okay, but what you need to be concerned about is This is here we assume that the minimum signal is also 0, right? But that's not the case, right? So what is the minimum signal? The signal here can go, this is, note that this is AC coupled, right? So the signal here, signal at this node can go VB minus VP, correct? So, which essentially means that I have to ensure that under this minimum signal condition also, if when the switch is supposed to be off, the switch turns off, correct? So hence that this you'll have to ensure that your under signal condition, that is your V over drive will still be equal to 0, right? So if the signal is Vp by 2, this is Vp by 2, then I have to add Vp by 2 to this V over drive thing. So which means that, so let me move these things a bit. Which means that, so this has to be equal to 0, which means your VGQ, to ensure that none of the signal passes through when the switch is supposed to be turned on, should be equal to VDD plus threshold voltage minus VP by 2, right? So that's how you go about designing this. Okay. So what we'll do is, so we'll stop the discussion on mixer here. In the next lecture, we'll get into the transmitter side, and then we'll see. I mean, we'll also talk about mixer from the transmitter angle a bit, and then take it from there. Okay.